Hey everyone! Today we're going to learn about gas mixtures and partial pressures. Let's start with an introduction. Now, please know I am going to have you star things I think you should write down, but let's go ahead and get started. So far, we've considered mainly pure gases, which means one substance in a gaseous state. That includes our stoichiometry. We've been converting from one pure gas to another pure gas. But how do we deal with mixtures of two or more different gases, such as the air? Air is a mixture of nitrogen and oxygen, carbon dioxide, water vapor. How do we deal with that? Well, John Dalton actually made an observation, and his observation stated the total pressure of a mixture of gases equals the sum of the pressures that each would exert if they were alone. So, what that means is that you would have to find the pressure of each individual gas and just add them up. So that comes into the term partial pressure. So this is more like a definition term. This is something I would be familiar with understanding. Remember, this is the pressure exerted by a single component within a mixture of gases. So, what is the partial pressure of nitrogen in an air mixture? So, Dalton made a law called Dalton's Law of Partial Pressures, which stated that PT stands for total pressure, is equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3, and so on for as many gases that you have. Now, the equation implies that each gas behaves independently of each other. Therefore, we can actually take the ideal gas law that we've learned and just reuse it. So here, what I've done is just rearranged that ideal gas law. So remember, we had PV equals nRT. What I've done is I've just divided both sides by V. So when you divide both sides by V, it gets rid of it on this side and puts it on the right. So that's all that's done here. You would use the ideal gas law to find the pressure of gas 1. P2 means pressure of gas 2, and you would just find them for all. And when you do that, again, add them up. So I have a couple examples where we'll go through these, and then some I'm going to have you guys do for homework. Here's one we're going to work through together. It says a mixture of 6 grams of O2 gas and 9 grams of CH4 gas, which is methane, is placed in a 15-liter vessel at 0 degrees Celsius. What is the partial pressure of each gas, and what is the total pressure within the vessel? So I'm going to go ahead and split this into two sides because we're working with two gases here. So to find the partial pressure, we're going to have to find it for oxygen, and then we're also going to have to find it for methane. So let's do oxygens first. One thing that we need to do is first we need to take this grams, we can't do anything with it, and change it to moles. So that's what we're going to do first. We have 6 grams of O2, and we're going to change it to the moles of O2 using molar mass. Now note this is O2, so I have to take my 15.999 and multiply it by 2, and you get 31.998 grams. And we're going to have to equal that out. Same thing with this methane. I have 9 grams of methane, so I need to take this 9 grams of methane and switch it over to moles as well. So 9 grams of methane. And no, if I'm finding the molar mass for methane, I have 1 carbon and 4 hydrogen. When I add that all up, you get 16.0426 grams, and you'll equal this out. So for oxygen, you get about 0.1875, and there's other numbers. And then for methane, you're going to get approximately 0.561. Oh, that's a 561 with additional numbers. And I'll write all those numbers down below. So let's get started. Remember, we are going to be using that ideal gas law. So we're going to use the already rearranged equation. It's easier. X equals, so X, remember, is our pressure. nRT, so our number of moles for oxygen, we found to be 18751171195 times our R value. Our R value is not going to change, 0.08206, times our temperature. So here our temperature is 0, but we need to change this to Kelvin. So you can either add 273, but I'm going to add 273.15 because I'm used to doing that. Then we want to divide this all by the volume. Note your volume has to be in liters. That's the important part. So my volume is 15. And now I can just plug this into my calculator, and you get that x equals 0.280201121. And I'm going to do the same thing over here for methane gas. So I'm going to plug in. Note that everything should stay the same. The only difference is your moles that you found for methane. So we got 56.561 0063207. Again, everything else in the formula is going to stay the same since we're working with a mixture. Even the temperature divided by 15. And when you solve for this one is going to be 0.83831888137. And then now we have to make sure that we're rounding to the proper number of sig figs. So note here, this one has 3, 3, 3. So we want our answer to have 3 sig figs. So here we have 0.280, and this is going to be pressure. So remember, pressure is ATM, and I did this one for my oxygen gas. Over here, we want 3 sig figs, so 838. And this is ATM because we're finding pressure. And then this one was my methane gas. Okay. Now, if it's asking you to find the partial pressures of each, so both of those are answers that you should have. So I'm going to go ahead and box those in. And then it's also asking for total pressure, so PT. Remember, total pressure is these added together. So when we add those together, we get about 1.12. Now remember, this is significant figures, and so sig figs, when you add them, are based on decimal places. So here, this is 3 after the decimal. This one's 3 after the decimal. So my answer needs to have 3 after the decimal. So 1.120 ATM is my total pressure of this entire mixture. And again, all I did was add those. This is a more practice. This is one that I'm going to have you guys do for homework. So this one you'll just do for homework and write in your notebook. Okay. Now let's move off from partial pressures and talk about mole fractions. Because each gas in a mixture behaves independently, we can relate the amount of a given gas in a mixture to the partial pressure. So what we can do here, what this is showing, is we can take the pressure of gas 1 and divide it by the total pressure. And that's the same thing as saying the mole of gas 1 divided by the total moles. So again, remember N equals moles. And if you see a little t, that means total. So the ratio of your mole of gas 1 divided by your total moles is called a mole fraction. And we can actually rewrite that as X for 1. And what we can do is we can actually combine these equations. And so what we're talking about is we're going to be using this equation right here. We can find the pressure of an individualized gas by finding our mole ratio and timesing it by our total mole. This is the one that I would write down, and this is the one you're going to use for your homework. Now, since this is a mole fraction, it can also be represented as a percent. So if you ever hear the word mole percent, it's going to be out of 100. So if you see 0.78, that's 78% of the air. So let's try to do an example and kind of explain it, and then hopefully it makes more sense. So I'm going to go ahead and actually write down our equation. So P1 equals N1 divided by NT times PT. So here we're going to find it says a study of the effects of certain gases on plant growth requires a synthetic atmosphere composed of 1.5 mole percent of CO2, 18.00 mole percent of O2, and then 80.5% mole percent of argon. And it says calculate the partial pressure of each gas in the mixture if the total pressure of the atmosphere is 745 torr. So, one thing to note is that we are still working with this ideal gas law, so we need to make sure that we change that torrs into ATMs. So, that's the first thing that I would do is make sure everything is in the proper units. So, we're going to do that, and we're going to take this 745 torr. I'll do it up here. Divide it by the 760 torr for 1 ATM to get my pressure, my total pressure. So that total pressure is going to be approximately 0.980, and I'll write the full amount down below. Okay. So now that I've got everything into the proper units, we have to plug things into our equation. It says, again, calculate the partial pressures. So we're going to calculate P1 and P2 and P3 because we're working with 3 gases. So we're going to go P1, which we're going to say is like CO2. So again, we're going to make P1 a CO2. What we're going to do is we have to find the moles of gas 1. So here I have 1.50 moles of gas 1. That's my CO2. And we're going to divide it by the total moles. So total moles. So I'm going to add up 1.5 plus 18 plus 80.5, and you should hopefully get 100. Now, remember when you add, it's based on decimal places. And so here, my fewest number is 1 after the decimal. So I'm going to write 100.0 so I don't get confused on sig figs. Okay. Then what we're going to do is we are actually going to divide these two things, and we are going to multiply it. Notice here we're going to multiply it by our total moles, and here, total pressure. And here it says our total pressure, we actually converted that up above here. So we're going to multiply it by that 0.9802631579. And we're going to equal that out to find our partial pressure of carbon dioxide. And when you actually equal that out, note here I have 3 sig figs. This one, I technically have 4 when I added it. And then over here I had 4. We are just going to go with that we have 3 sig figs. So here we have 0.0147. Again, we're finding pressure. It's always in ATM. And then this is of my CO2 gas. So that's one of my partial pressures that we're going to calculate. Now we're going to find our partial pressure of our gas 2. And our gas 2, we're going to say is O2. Again, we're going to follow these same steps. We're going to say the mole of gas 2, so that's oxygen, is 18.00 moles. Okay, we're going to divide that by the total amount we have here, which is 100. That's not going to change. And then we're still going to multiply it by our total pressure. And when we equal this out, please note, here I had 4 sig figs because of my moles. Here, when we added it, that's why I added this 0.0 for my 4 sig figs. And then technically this one has 4 sig figs. So I'm going to make sure that my answer has 4 sig figs. Now from there are a couple options that you could do. You could actually solve for P3, which is our argon gas, the exact same way. Or you could note that all of these have to add up to my 0.980 number. So you can actually just add these two values up and subtract it from the total to figure out what's left. But I'm just going to go ahead and show the math behind it just to make sure you guys have it right. So here we're going to notice that I have 80.5 moles. Again, nothing else is going to change but that 80.5. Oops. And we're going to multiply it by the same total pressure. Okay. And when you guys go ahead and equal that out, we're going to rank it to 3 sig figs based on the numbers that I'm given. So 0.789 atm of argon. Here I have a more practice problem. I'm going to have you guys do this one for homework, and then on here I'm going to have you do this one as well. If you have any questions, please make sure that you guys come up and ask. Remember, I am available to you, and we will go over those practice problems as a class tomorrow before I give you your worksheet. If you have any questions, again, ask, and I hope you guys have a great day.